Good day, esteemed colleagues. My name is Dmytro, and today I will be presenting the results of our study titled Fourier Model Fitting for Vibration Analysis of Car Wheel Suspension Enhanced Damping System. In the study, we focused on analyzing vibration signals from a car suspension system using Fourier Model Fitting. Here is a brief overview of the structure of my presentation. First, I will discuss the significance of the automotive industry and the impact of the study on Ukraine. Then we will move on to the methodology of the experiment, followed by a detailed explanation of the theoretical aspects of Fourier analysis and data processing results. We will also review the calculation of Fourier coefficients and truncated series representation. Finally, we will cover computer modeling and the conclusions of the study. Let's start with the context of the study. The global automotive industry has been growing rapidly over the past few decades. Although Ukraine lags behind due to various economic and political factors, the potential for the transport sector to contribute to the national economy is enormous. For example, before the war, the sector accounted for about 7% of Ukraine's GDP. Recent advancements in the automotive field highlight the growing importance of information modeling technologies to analyze and predict the impact of operational factors on vehicle systems. Studies suggest that suspension systems, which are critical for improving ride comfort and vehicle stability, require enhanced methods of analysis to ensure optimal performance under various conditions. Controlled suspension systems, combining passive and active elements, have been widely researched for their ability to improve the smoothness of motion. The suspension system is a critical component that affects both ride comfort and handling. So, optimizing it through vibration analysis is a highly relevant topic. The goal of the study was to analyze the vibrations of the car suspension system using the Fourier series decomposition method. This approach allows us to identify the dominant frequencies that influence the suspension's performance and propose ways to optimize the system for improved ride comfort and handling. Now let's move on to the methodology. The experiment was conducted using a specially designed test rig equipped with accelerometers to capture vibration signals from the suspension system under different conditions. Wheel rotation frequencies ranging from 10 to 40 Hz and tire pressures from 1.0 to 2.5 atmospheres. Before applying the Fourier method, the data underwent preprocessing, including detrending, removing any linear trends from the signals, and normalization, bringing the signals to a common scale to ensure more accurate analysis. Now let's briefly discuss the theoretical part. The Fourier series allows us to represent any periodic signal as a sum of sinusoidal components with different frequencies, amplitudes, and phases. Using the Fourier coefficients, we can analyze the contribution of each harmonic component to the overall signal, which is essential for understanding the dynamic behavior of the system. Regarding data preprocessing, first we performed the trending to remove any linear trends caused by sensor drift or slow changes in system performance. This ensures more accurate signal analysis. Next, we applied normalization using the z-score method, which brings the signals to a common scale, allowing for correct comparison of different datasets. Normalization allowed us to eliminate any bias from different amplitudes across experimental conditions, making the signals ready for Fourier analysis. The preprocessed signals after the training and normalization provided clear insights into the vibration characteristics. The power spectrogram and instantaneous frequency estimates show the effectiveness of our preprocessing approach, ensuring that the signals are clean and ready for Fourier model fitting. After preprocessing, we calculated the Fourier coefficients for each harmonic component of the signal. This allowed us to identify the dominant frequencies that contribute to the overall vibration pattern. On the slide, you can see the magnitude spectra, which illustrate how different frequencies contribute to the dynamic behavior of the suspension system. To further simplify the model, we used a truncated Fourier series, considering only the 5 most significant harmonics. This approach reduces the complexity of the model while still capturing the essential characteristics of the signal. The graphs show the reconstructed signals for channel 6 and channel 7, where only the 5 most important harmonics were used. For model validation, we calculated several goodness of fit metrics, such as R squared and RMCE. This matrix confirmed that the model aligns well with the experimental data. Additionally, a visual comparison of the reconstructed signal with the experimental data further validates the model's accuracy. To further validate the model, we analyzed the relationship between the signals recovered from channel 6 and channel 7 using a cross spectrogram. This tool allows us to explore how these signals are correlated across different frequencies and time intervals. The cross spectrogram highlights the regions of strong coherence between the two channels, providing insights into how the vibration patterns are shared between different points on the suspension system. The high coherence regions indicate common oscillation that contribute to the overall vibration behavior, which is the model successfully captures. The next step was computer modeling. We created a detailed CAD model of the shock absorber in SolidWorks and performed a stress-strain analysis on the rubber element. A finite element mesh was generated to analyze the stress-strain state of the rubber element in the shock absorber. The mesh had a global element size of 5 mm with a tolerance of 0.25 mm, ensuring high precision in the simulation. The results of the stress analysis revealed that the maximum stress of 3.43 megapascals occurs near the fixation point of the rubber element. This information is critical for understanding the areas of the shock absorber that are most susceptible to stress during operation. The analysis of the safety factors shows that the minimum safety margin for the rubber element is approximately 4, which indicates that the element operates within a safe range under the applied conditions. The deformation results demonstrate that the maximum deformation of the rubber elements is 11%, occurring near the fixation point. This result confirms that the shock absorber can withstand with the applied loads without significant deformation, maintaining its structural integrity. The analysis of the actual displacements shows that the maximum vertical displacement of the rubber element is 12.3 millimeters. This occurs at the lower edge of the outer cylinder, with the rubber element experiencing downward displacement under the applied pressure. The axial force on the rubber element was calculated to be 1.89, confirming that the shock absorber is capable of effectively distributing the loads without excessive deformation, ensuring optimal performance. In conclusion, our Fourier-based approach allowed us to thoroughly analyze the vibration behavior of the suspension system. We identified the dominant frequencies that influence ride comfort and validated the accuracy of the model using experimental data. The findings of the study can guide further optimization of suspension parameters to improve vehicle performance. Thank you for your attention. If you have any questions, I will be happy to answer them. Just feel free to contact me.